Hey guys, I hope you're having a good day today. This is Grant and I'm back again with another video. And today we have a flux problem, and it asks us to find the flux of this vector field f, where f is this nasty thing, x squared y, xy squared minus 3z to the fourth times e to the 3x, and ln y to the fourth x cubed plus 12/7 y squared through the surface S. So through the surface S, where S is a sphere of radius 4, with z less than or equal to 0, y less than or equal to 0 as well, and outward orientation. Note that all three surfaces of the solid are included in S. Okay, so let's draw a picture here. We have this surface S. S is a sphere, and it's given, and these bounds are negative, or z less than or equal to 0, y less than or equal to 0. So when z is less than or equal to 0, it's just an area below the xy plane. When y is less than or equal to 0, it's the area to the left of the xz plane. So what we're talking about here is a sphere, radius 4, that looks like this, right? Below the xy plane and to the left of the xz plane. So that is what we have here. Sphere has radius 4. Okay, well, so we're looking for flux, right? Obviously, this vector field is a nasty old thing. How we would usually do this is, what we would do is parameterize each of these surfaces, which, by the way, there's three surfaces. There's the outer surface, this surface here, and this surface here. And we'd have to do three separate surfaces, reparameterize them in sphericals, and find a normal vector. It'd just be very nasty. We'd compose that with our spherical, with our parameterization of sphericals, and it would just be very ugly. But instead, what we can do is use the divergence theorem of Gauss. The divergence theorem of Gauss, which has to do with flux. And it says, well, flux is just f dot ds. Well, the divergence theorem of Gauss says, well, this is equal to the divergence of f dv over the region R, provided that S is the boundary of the region, which it is, right? S is each of the three surfaces, so it's definitely the boundary of the region in this case. And it also is provided that f has continuous first-order partial derivatives. Looks like it does. So yeah, this should work out, right? The divergence theorem of Gauss. All we need is the divergence of f dv over the region R. Well, since this is a sphere, we should probably use sphericals. So this says this is a sphere of radius 4. So rho is going to go from 0 to 4. Phi is going to go, remember phi is just an angle from the positive z to the negative z. It's going to go, it doesn't go from 0 to pi over 2, it goes from pi over 2 to pi. I wrote that wrong. Pi over 2 to pi, right? Because, again, this is below the xy plane. And theta, in this case, y is negative. So this is going to go from pi to 2 pi. If we drew this in the xy plane, it would be wherever y is negative. So this, obviously, that's x, and that would be y. So this would go from pi to 2 pi. Okay, sounds good. Now we need to find the divergence of f. Well, that's just del dot f. And del, remember, is the del operator. Partial with respect to y, x, y, and z. And we're going to dot this with f. And f is this very complicated looking thing. But all we have to do is take this component with respect to x. So that's should just be 2yx, right? 2yx. This, with respect to y, that doesn't have a y in it, but that does. So that's 2yx again, right? And this with respect to z, there's no z, so that's just 0. So the divergence of f is ultimately 4yx. Okay, that's nice. We need to remember our transformations, our Cartesian transformations into sphericals. X is rho sine phi cosine theta, y equals rho sine phi sine theta, and z is cosine phi. Should be, is it rho cosine phi? It doesn't matter really here. I think it would be, z is rho cosine phi. Doesn't really matter here anyway because we just have x's and y's. Anyways, all right, so now we can set up this integral. Flux. This is the triple integral of the divergence of f, which we found to be 4xy, which is really 4 times, well, that's going to be rho squared, sine squared phi, times cosine theta sine theta. And then remember, we need to remember the Jacobian here. We need to remember the Jacobian here. We're going to go with respect to rho, 0 to 4, d phi. We said that was what, pi over 2 to pi, and d theta, pi to 2 pi d theta. All right. This integral looks a little challenging, but it really wouldn't be as challenging or as nearly as hard as doing it the other way. So we are going to evaluate this in the next video. But this is ultimately, setting this up's half the battle, right? Got to remember Divergence Theorem of Gauss. It works if the orientation is outward, which it is. S is a boundary surface of the region. It is. Continuous first order partial derivatives, they have that. So this should work. We will evaluate this integral, this triple integral, in the next video.